Hey everybody, I hope you're all having a safe and fun Easter. It is Saturday night here at my house, and I thought I'd sit down, get away from my family, and show you a couple more reactions that we can do. So there's two videos, including this one. The first is going to be the reactions of carboxylate salts, and then we're going to get a little bit more into the reactions of some nitriles. And then the last video I'm going to do, I like to call cleanup. There's a couple of weird reactions that I want to show you before we end this section and go on to the next unit, which deals with reactions at the alpha and beta carbon with respect to the carbonyl. So, in order to do this, let's talk about really the one that no one cares about in the acid derivative family, the salt. The salt is so unreactive and so unambitious that the more type A personalities in the acid derivative family, like the anhydrides or the acid chlorides, really don't like to be around it. It's usually sacked out on a couch, either working off a beer buzz or a high, and just doesn't do a whole lot. So probably the first and most important thing we can say about the carboxylate salt is we can add an external acid source to it and go back to here. Go back to the protonated acid itself. Now remember, each of these derivatives, you could go backwards, you could go to the derivative in one step from the acid and back to the acid from the derivative also in one step. Now, if I'm not going to show you the mechanism for this, because if you can't figure it out, damn, we've got trouble. Here's another one that you've seen. You can take the carboxylate salt and you can react it with an acid chloride. And what happens is you wind up with this. You wind up with the asymmetric anhydride. Now, I am probably the only person on the planet who gives a shit about asymmetric anhydrides because I had to work with a lot of them as an undergrad. So really, that's what we need to talk about with the salt. It does those two things. So now what I would like to do is start talking a little bit more about the nitrile. This fits in the acid and acid derivative family, because most of the reactions, when you do a reaction on a nitrile, these tend to go towards making acids, salts, and if you're really slick, occasionally an amide. Oops, sorry. All right. So let's take a look. You have seen some of these. I just feel like it would be worth our time to go through them once again. All right? So let's take a look at one of these. So we can react the nitrile with lithium aluminum hydride followed by water, and it would turn the nitrile into an amine. You can do the same reaction using platinum and hydrogen gas. You can hydrogenate this. They do hydrogenate. Most of the time you want to avoid using heteroatoms in your hydrogenations because these can sometimes spoil the catalysts. The pairs of electrons on the heteroatoms can get into the catalyst and prevent the reaction from occurring that you're really interested in. But that too will take you to the free amine. Now, we've done these mechanisms, I think just last video or maybe the one before, so I'm not going to march through them again. Oops. Sorry about that, folks. Someone in my house decided to take that opportunity to start screaming. All right, so again, we've seen these reactions recently. I don't see the need the frog march through them again. I'm just going to remind you of them. Acid, water, and heat to turn a nitrile into a carboxylic acid. And a nitrile with base, water, and heat to turn it into the salt. Okay, now, there's another one that we've done, that you have done, that you just may not think of it this way, and this is called a Ritter reaction. And it looks like this. A nitrile plus a tertiary alcohol, that is important, done with acid and some heat. And what you get out of this is the highly substituted amide. This was the mystery reaction we had you guys doing at the beginning of the semester. So I'm going to run through this mechanism really quickly. I know my lab saw it. I'm not sure if Dr. Lewis's did, but it wouldn't hurt for us to review it again. The first thing that happens in these is we take the tertiary alcohol, we protonate it from the external acid source, and we get this. And what do you know about tertiary cations? They're pretty stable. And you can form this. Now, we can have the nitrile attack that cation and get you here. Water comes in as the nucleophile, attacks that carbon, breaks open the pi bond. You get here. And this is what you make. You do a deprotonation with water. And I apologize, this is kind of becoming a Mobius mechanism, which puts you here. All right, this is called an amidic acid. And it tautomerizes, just like a keto-enol tautomerization. It tautomerizes to give you the amide. Now, if you weren't happy with the tautomerization idea here, you could very easily start from, say, this juncture and figure out the proton transfer and how the electrons move around, and you would not be wrong. Okay, so that's it for this one. There's a couple more of these nitrile reactions that I want to show you, and this one is a weird one. This one involves reacting a nitrile, and I am going to pick a Grignard, phenylmagnesium bromide, in the first step, and the second step, acid and water. Okay? Now, when we do this reaction, the product you get is a ketone. A little weird, so I want to just work through a couple spots of it so you can kind of get an idea for the mechanism. This carbon with the bond is right here, okay? And then hopefully, obviously, you can see that phenyl ring is right there. Now, the mechanism of this definitely comes down into two different steps. The first one being, and probably not that shocking, the reaction of the Grignard onto the nitrile carbon, opening up the carbon-nitrogen pi bond, or one of them anyway. This is not reversible, which puts you here. So this is step one. Step two comes into play with this nitrogen anion grabbing a proton off of the acid. Now, I can hear some of you saying already, but Dr. Weigel, that doesn't make any sense because Grignards don't do well in water or acid environments. And I'd say, you're right, but you'll notice I broke this up into step 1 and 2. So now we're here. And all would be well with the world, but you're not going to stop at this imine because there's more acid around. Pair of electrons grabs the proton. You're here. Now, while I'm drawing this in, let me tell you something. I have a lot of students worry about how important is it to know that a step is reversible? Because I'll be honest, sometimes I forget to show you the reversibility, and sometimes it's not that important. And what I will try to do from here on out is, if it's important, I will really emphasize the reversibility part of this. If it is not important, then I won't, but as always, feel free to ask me, either in the comments here or through email, anything you'd like. All right, so water attacks the imine carbon, putting you here. Where you've got an NH2 next to the OH2. All right, pair of electrons. You know what? I'm not going to finish this because I have faith that you can. I'm not even going to talk about this anymore. So what I want you to do as a practice for yourself, I want you to try this. Figure out from here how we get to the ketone. All right, that's it for this video. I have one more coming, which is sort of the weird reactions, but I want to talk about them. So have a great Easter if you haven't already, or your favorite spring holiday of choice, and I will see you soon.